All right, so last time we talked about Gaussian elimination or triangle form of elimination, which means if you have a system of equations in three variables, as we have here, and you form an augmented matrix to begin with, and do row operations on it, you're eventually going to end up with a form of 1 for your x variable, some number for y, and some number for z, 0 in the second equation, 1, some number, and then 0, 0 with a 1, and then whatever your values ended up being. And from here, we did back substitution where 1 equals c, so you plug, or excuse me, x, y, z, z equals c, you plug c in for z and use that to solve for y, and then you plug z and y in and use that to solve for x. So this is called triangle form or Gaussian elimination. There's another form of elimination called Gauss-Jordan. Elimination. And all that, the only difference is the first step is the same, where you get this triangle form where you have 3 zeros in the bottom and a string of ones. But Gauss-Jordan has us go ahead and continue to produce zeros in all the places except for this diagonal row of ones. Then my augmented matrix ABC would result in A being directly taken out of the matrix. X equals A, Y equals B, and Z equals C. So the truth is, Gauss-Jordan is a bunch more work to get the upper triangle in your matrix. And back substitution is easy enough that most of the time, if all we're doing is trying to solve a system, we would use just Gaussian elimination. But the Gauss-Jordan form of a matrix is uber important in some other applications of matrix operation. So after we do a little bit of solving with Gauss-Jordan elimination, we'll talk about types of solutions. And this you have seen before, except for one kind of twist on one of the solutions. When there are three variables, it's no different than when there are two variables, two equations with two variables. Same thing with three equations and three variables. You'll either end up with one solution, and end up with an ordered pair, or excuse me, an ordered triplet, x, y, and z solution. There could be no solutions. You get to the end of your, either way, your Gaussian or your Gauss-Jordan elimination, and you discover that, say, for example, 2 equals 12, which of course is only true in Crazy Town, and so we don't live there, and we throw that value out. There's nothing that solves that system. Then one other is the infinite solutions. And you've seen that before. You get to the end of solving a system and you find out that, or you have an expression or an equation like 2 equals 2, which is always true. And since 2 equals 2 is always true, that means you have infinitely many solutions. We'll look at one more version of this called parameterized. Parameterized. I think there might be an E missing in here. Parameterized solution, which is a form of infinitely many. So let's go ahead and use Gauss-Jordan elimination on this system to discover our value for x, our value for y, and our value for c that makes this system true. So first thing we want to do is convert this to a matrix, and I'm going to move my problem over so I have a little bit more room to work. So I think what I want to do is, remember one of our operations is that we can switch any two rows. And so I'm going to go ahead and switch row 1 and row 2. Since I want to get a 1 up in this upper left-hand corner, I'm closer to getting a 1 in the upper left-hand corner by just moving this middle equation to the top. So I'm going to go ahead and do that. And that means I have a -1. Well, maybe what I'll also do is when I do that, I'm going to multiply row 2 in this case. I'm going to multiply negative 1 times row 2. And so that'll give me a positive. So the opposite of the opposite of negative 1 is 1. The opposite of negative 2 is 2. The opposite of negative 4 is 4. And the opposite of negative 1 is 1. Okay, so that kind of killed two birds with one stone. I think it was probably pretty clear what I did, and not too much that I would lose you. Then what was my first row is now my second row, and so the coefficients are 4, 9, 16, and 2. And then now my third row I'm just going to keep in the same place, so that's 2, 4, 9, and negative 5. Put them in my brackets because these are matrices, and then it's augmented, so I'll put the dotted line. Okay, now I'm well on my way. I already have a 1 up here in this triangle, so I'm really good to go. So remember last time when we talked about this, we want to use this 1 to turn both of these rows into zeros. I can do them in one step, which I think I will actually, rather than 2 steps. So I'm going to add to this row, I'm going to add negative 4 times row 1. So the row I'm going to change is this middle row, and I'm going to change it by adding negative 4 times row 1. And then I'm going to change the third row by adding negative 2 times row 1. So I'm going to use this 1 to change both of these into zeros. So let's see if I can do this. Well, I know I can, but let's see if I can do it without making any mistakes. So the row I'm not going to change at all in this operation or this iteration is this first row, so I'm just going to write it down so I don't make any mistakes. Then negative 4 times 1 is negative 4 plus 4 is 0. 2 times negative 4 is negative 8 plus 9 is 1. 4 times negative 4 is negative 16 plus 16 is 0. And 1 times negative 4 is negative 4 plus 2 is negative 2. All right, continuing the pattern. 1 times negative 2, I might cross this out just because I'm done so I don't get myself lost and confused. 1 times negative 2 is negative 2 plus 2, 0. 1 times 2 times negative 2, negative 4 plus 4 is 0. And 4 times negative 2 is negative 8 plus 9 is 1. This looks really good. I already have my diagonal and I have a 0 here. This is looking good. So let me keep going. 1 times negative 2 is negative 2. Take away 5 is negative 7. Okay, so that's 2 steps or 2 row operations in one step. And I think I've executed it properly. So let's continue on. And before I do, let's make a game plan. So remember, we changed this order before. We sort of want to do the same thing. We want to change in this order. Now the fact that this one's already a 0 is great. That's going to work for us. It won't change. It'll stay a 0. But I want to change this 4 first and then move on to the 2. So duplicating the order we learned before. Let's do a row operation on row number 1, and I'm going to add, since 4 is what I want to get rid of, it's row 3 I'm going to use. I'm going to use the 1 in row 3. So I'm going to add negative 4 times row 3 to this first row. That means I want to go ahead and write down the rows. I'm not changing. 0, 1, 0, negative 2, and 0. I better not write it that tight. 0, 1, 0, negative 2, and 0, 0, 1, negative 7. And now I am not in danger of accidentally altering that row. So let's do the first row operations. So I have 0 times negative 4 is 0 plus 1 is 1. 0 times negative 4 is 0 plus 2 is 2. And that's okay because I was expecting to still have that 2. And then 1 times negative 4 is negative 4 plus 4 is 0. And now finishing up my row, negative 7 times negative 4 is positive 28 plus 1 is positive 29. Okay, one more operation. I need to get rid of the 2. So I'm going to use row 2 and I'm going to add a multiple of row 2. And that multiple would need to be a negative 2 to get rid of this positive 2 by converting it to a 0. So let's write down the rows I'm not changing. Okay, and it's augmented. And then I'm using row 2, so I have to be really careful to make sure I keep using row 2. 0 times negative 2 is 0, plus 1, 1. 1 times negative 2 plus 2, 0. 0 times negative 2 is 0, plus 0, that stays 0, and then negative 2 times negative 2 is positive 4. Add to 29 is 33. And now we see the beauty of Gauss-Jordan method of elimination, because I have an x, my y, and my z. Let's label these. This is the x row, the y row, and the z row for each of my original equations. And I can tell just by glancing that x and y have been y and z have been zeroed out. So x equals 33 in my solution. Y is negative 2. And z is negative 7. So the triple, the ordered triple, 33, negative 2, and negative 7 is the solution to this system of equations. And in this case, I had one solution as a type. And bam, just in the nick of time, I get a new equation. Or a new system. So we're going to solve this system again, Gauss-Jordan elimination, and heads up, we're going to get one of these other types of solutions. So let's see. Let's go quickly. I'm going to keep this first equation where it is because it already has a 1 in the upper left-hand corner. So my coefficients would be 1, 3, 4, and then my constant would be 8, and then 4, negative 2, negative 1, and 6, 8, negative 18, negative 19, and negative 2. So now I have an augmented matrix that I can use row operations to solve this system. So again, we're going to do Gauss-Jordan elimination. So I want to use my pattern, and I know the pattern is to change first these to zeros, and then change, whoops, went the wrong direction, these to zeros, right? But I'm going to take those out so they don't confuse us for right now. Okay, so I'm happy with my 1 right here. So the first thing I want to do is change this to a 1 and change, a 0, and change this to a 0. So for the second row, I'm going to add negative 4 times row 1, because that's the one that has my 1. And for the third row, I'm going to add negative 8 times row 1. And I think to save us some time, I'm going to go ahead and do these calculations so they'll suddenly pop up off air. Bam, there you go. So I need a 0 here at negative 42, which means I'm going to add a multiple of row, I'm going to use row 1 because, or I could use row 2 and not have to multiply by as much. So I'm going to use row 2. And what I need is a positive 42, so I'm going to multiply 14 times negative 3. That'll give me a positive 42 plus positive 42, take away 42 is going to give me a 0. Again, I'm going to do that off air. And there. Okay, so now I want to convert this to a 1, which means I would want to multiply this row by positive 1/14. That means I'm going to divide negative 17 by 14 and 26 by 14. I'm going to get fractions. That happens all the time in matrices. You're going to have a chance to get really good with simple arithmetic and really good with simple adding fractions, adding and subtracting fractions. But luckily in this case, we don't actually have to do that, because look what just happened. This is our x column, right? So if I could get these two numbers to be zeros, then I would be able to say what x is. This is my y column. Again, if I could get this to be a 1 and this to be a 0, I'd be able to pluck it right out. But this is my z column. I'm done here. And what I have is 0 equals negative 12. That's crazy. That never happens in our real world, our sweet little real world. So this system has no solution. So crazy town is crazy town. Even when you have a system of equations, it's still crazy. 0 is never going to equal negative 12. So at this stage in the game, we already know that the system has no solution. There is no combination of x, y, and z that will make all of these three equations true statements. If, on the other hand, I had calculated this entire matrix, and when I got to the end, I had something that was true, for example, 2 equals 2, if this had happened, then I would have been able to say that there were infinitely many solutions. And what that means is, since I got to an identity, when I solved the matrix, I ended up with an identity. All that tells me is that every x, y, and z would make this true, or in this case, every x would make this true. And so there are infinitely many solutions, even if they're different y and z's. There are infinitely many x's I could choose from, and x will always make it true. Any x will make it true. So the last thing to look at then is the no solutions with a parameterized solution. And here you see an example of that. If you, on close inspection, you can already see we've broken a rule for solving systems. I have 1, 2, 3, 4 variables I'm looking to solve, and I only have 3 equations. And we know you have to have the number of equations that you have variables. But that's okay, because when you parameterize a solution, you can adjust for that. So let's have a look at this. If I made the matrix for this system, it would be 3, negative 8, 19, and negative 12. And 6. For the second row, I get 2, negative 4, 10, 0, because I don't have a w, and negative 8. And for the last row, I get 1, negative 3, 5, negative 2, and negative 1. All right, and if I go ahead and finish this out, which I'm about to do, so you'll see the answer pop up. There it is. So let's see what we have. Notice I didn't get to any kind of resolution on my W variable. I did get the row reduced, or the most reduced double triangle form of Gauss-Jordan elimination, but I still have values that are represented by my W variable. Let's write what we have. If I put this back into an equation, I get that x plus 14w equals negative 25, y plus 2w equals negative 3, and z minus 2w equals 3. Now I can solve each of these equations for the variable x, y, and z if I had, which gives me, let me put them in a different color, x equals negative 14w minus 25, y equals negative 2w minus 3, and z equals 2w plus 3. And since I have something that represents x, y, and z, believe it or not, I can write this sort of as a ordered triplet. I could say x is minus 14w minus 25, comma, that's my x ordinate. My y would be negative 2w minus 3, and my z would be 2w plus 3. And so each of my values, or each of my ordinates, this would be x, this would be y, and this would be z, each of them is dependent on what I choose for W. If I choose 2 to be W, then I'm going to get one set of X, Y, Z triplets. If I choose -9 to be W, I'm going to get another set of X, Y, Z. Since I can choose any value for W as long as they're the same value in each of the ordinants, then I have infinitely many solutions. And so that is another version of parameterized solutions to a system of equations. Oh, I think I'm done talking. So by the way, this last problem is number example 7 in section 6.1 of your textbook, where you can see all the row operations worked out. I just didn't think you needed to hear me go through another set of row operations. What I really wanted to explain was how to evaluate when you get this kind of a final set of values at the bottom of your matrix. So there you go. The Gauss-Jordan form of elimination, which is an addition to the Gaussian form of elimination, lower triangle, upper and lower triangle. This is called reduced echelon form. Oh, excuse me, this is called echelon form, and this is called reduced echelon form. 3 different kinds of solutions. You can get one solution where there is an exact value for each of the variables in the system. You can get no solutions when you get some crazy outcome at the end. And you can have infinitely many solutions when you either come up with an identity at the end or when you get a parameterized outcome. So there you go.